Let us graph
Try that. Now, if it doesn't work, I'll load you from with. You don't really need it for what we're doing right now. Okay.
let's graph this.
But like, everybody's able to get into my last class, right?
Okay, so we're going to go ahead and graph this here. Now this is already factored. And it's awfully nice when it's already factored because we can immediately read right off the graph what the roots are going to be, and we can figure out pretty quickly what the end behavior is going to look like. Because we can figure out the degree, we can figure out the lead coefficient. So first of all, the degree, well, let's see. If we were to multiply everything out, this is x squared 2. This is a first degree polynomial here with no power up here. So that's 2 plus 1 is 3. This is a fourth degree root. So 2 plus 1 plus 4 is 7. Which is odd. That's all we care about. The lead coefficient, well, if we were to multiply this all out, there's nothing, there's just an implied 1 up here, and there's 1s in front of everything. The lead coefficient is actually also just going to be 1, which is positive. So we remember that the end behavior for an odd degree polynomial that has a positive lead coefficient, this is going to fall to the left, rise to the right. If you scroll back through your notes, you'll see that this is the case. Also, we need to look at the roots and their multiplicity. So here, this one is actually going to be a root of x equals 0. Because if you think about it, x squared could just be written as x minus 0 squared. So this here is a root of x equals 0, and thus, or not thus, its multiplicity then is going to be 2 because it's x squared. There's a squared up there. And 2 is an even number. So that means when we graph this, it's going to just approach the x-axis, but then it's going to go back, and it's just going to touch the x-axis and go back the way it came. Over here, x minus 3, this is actually a root of x equals 3. And then you can see up here, there's no power written, which means there's an implied power of 1. So this is going to have a multiplicity of 1. Finally, up here, we're going to have x plus 2 as the factor. So x is going to be equal to, the root itself is going to be negative 2. Basically, you flip the sign on it. And then we can see it clearly has a multiplicity of 4. So we are now ready to graph this thing. We are now ready to graph. The only thing you might want to get perhaps is the y-intercept, which you get by plugging a 0 in for x and figuring out what this becomes. But that would clearly actually just end up being 0. This thing's going to 0 it all out. So finding the y-intercept is the same, even for wild polynomials like this. So now let's label some of the key points. Negative 2 would be maybe right about here. Zero, of course, is going to be right here, an x value of 0. So the x value of 0 is also a 0 on the graph. That's just a coincidence. It's also a root. And then 1, 2, maybe positive 3 is something like right here. Now we remember this thing is going to fall to the left, rise to the right. So all the way out here to the left, it's going to be going downwards like that. And so it's going to do that. And then when it gets to this root of negative 2, since this thing has an even multiplicity, it's just going to touch it and come back down. Let me draw that a little better. It's just going to touch it and come back down like that. But then it needs to come back up because it has to come up and touch the x-axis again at x equals 0. So it's going to do something like that. And then at an x value of 0, that also has an even multiplicity. So it's going to try again to cross the x-axis and it's going to fail. And then finally, when x is equal to 3, that has an odd multiplicity. So it is going to come back up and it's actually going to cross through the x-axis this time. And then it never goes back to the x-axis because we've run out of roots. Also, this thing needs to rise to the right and fall to the left. So now graphing, in general, you won't be given a polynomial in factored form. So you'll need to factor it using the techniques of this chapter. Maybe generate the rational roots test, get all the possible rational roots for a polynomial, and try them all out with synthetic division and see what you can divide out. And keep following that process, like the examples we did last time, until you have it fully factored. And then you can, once you have it factored, you can easily read what the roots are going to be, what the end behavior is going to be based on the degree and the lead coefficient. Okay, so we are now going to look at the next chapter, next section, I should say, rational functions. And now what we're going to realize is that embedded in the word rational is the word ratio. Ooh. The word ratio is in there. And when you think of a ratio, you think of division. You think of one thing divided by another, which is going to be exactly right when it comes to rational functions. A rational function is simply one polynomial divided by another. It's one polynomial divided by another. In fact, once you recognize that, it's kind of useful to recognize the degree of the top polynomial and the degree of the bottom polynomial. So let's say you had a rational equation. These are just some examples you could have. For x squared plus x plus 1. That's an example. You have a cubic or third degree polynomial divided by a second degree polynomial. Now you have to be very careful. You have to be very careful because this new thing we've created is not a polynomial. It is constructed of polynomials, but it is not itself a polynomial. Kind of like how a notebook is constructed of pieces of paper. There's a lot of pieces of paper, but a notebook is not itself a piece of paper or paper. A notebook is made of those things, but we've given a name to this new thing that transcends from that. Similar idea here. So this is not a polynomial. This is a ratio of two polynomials, one on top divided by one on bottom. And so it doesn't take a lot of imagination to start really generating some rational functions. Oh, a 15th degree polynomial on top. And then on bottom you have a 15th degree polynomial. On top, you just have the number 3, which is just a constant. But what we're actually going to tell ourselves is that this is a 0th degree polynomial. On top. That's what we're going to say. And that's exactly what it is. That's not just something we're making up. So a rational function is no more than one polynomial divided by another. Well, this immediately can create problems. Namely in the form of the domain. If you think about it, you have a polynomial on bottom, and we've just spent several sections now trying to basically solve polynomials. We're trying to factor them and figure out what their zeros are, their roots. A root is an x value that can be plugged into the polynomial that causes it to go to 0. So if you have, let me show an example. If you have a rational function on bottom, let's say you have this polynomial. This creates some serious problems, mostly because this denominator can go to 0. I mean, if you remember factoring a little bit, x squared minus 5x plus 6 can be factored as x minus 2, x minus 3. And then what this means, x values of positive 2 and positive 3 make the denominator go to 0. You plug a 2 into this polynomial here, it might do something on top. It may not be 0 on top, but it's going to be 0 on bottom, which is going to be a huge problem, because dividing by 0, you remember, is kind of one of our unforgivable curses in math. And there's going to be several: dividing by 0, taking the square root of a negative number, and what we're going to see just in chapter 4 here, taking the logarithm of a negative number. So it's one of the unforgivable curses. It's a one-way ticket to Azkaban if you use it, simply because dividing by 0 is not defined, and we talked about that. This then means, in turn, that any x value which causes the denominator to go to 0 is not in the domain of the rational function. I'll repeat, any x value that causes the denominator to go to 0 is not in the domain of the rational function, because the domain is just the collection of all values you're basically allowed to plug in to the x variable, all values of the independent variable that you're allowed to utilize. Well, if it makes the bottom go to 0, you're not allowed to utilize that. So, in other words, for this one, the domain here would be all x values except x equals 2 and x equals 3. So for this function here, that's going to be the domain. If you wanted to write this in interval notation, you have to be a little tricky. You have to be a little bit cute about it. We need to go from negative infinity to positive infinity, but we need to exclude 2 and 3. So the way it would look, the domain would look like this. D for domain. You'd go from negative infinity, but then you'd come up to 2 and you'd have to stop, use a parentheses there. Then every number between 2 and 3, and there's an infinite amount of numbers, 2.5, 2.7, 18, 24. Every number between 2 and 3 is allowed. So you union the interval from 2 to 3. And then you got to skip over 3. So we use a parentheses on the 3. We union it. And then we can do every number greater than 3, strictly greater than 3, all the way on up to infinity. Positive infinity. So that's going to be how we handle the domain of these rational equations, these rational functions. Simply put, we gotta figure out what makes the bottom go to 0 and throw it out. There's a few other things that are going to kind of be a fly in the ointment here whenever we start graphing these rational functions. We have to talk about asymptotes. Asymptotes. Now, an asymptote is going to be a line. This will be a line that the graph of the rational function will approach but never quite touch or cross through. So it's going to approach but never quite cross through that line. It's an invisible line too. We don't actually physically draw it. We might draw a dashed line for it because the dashing makes you think that's just so we can see where this asymptote is, but without ever actually having to approach it or actually draw it physically on the graph. So it gets close, but never quite crosses its own asymptote. Every graph does that. And so, as you can imagine, there's going to be, you think of all the different lines you could make. All the different lines, you could make horizontal lines, you can make vertical lines. You can also just make regular old lines that, have slope and a y-intercept, something like that. All of those could be asymptotes to your rational function. So let's look at them case by case. A vertical asymptote, straight up and down line. Let me draw you a nice little picture. Basic idea of a vertical asymptote here. How about you have something that's doing, oh, not a line. Something that's doing this. There's going to be a hidden asymptote here, a vertical line that it just can't quite cross. I'll represent it with a dashed line. And the dashed line isn't actually on the graph of the function. This is just to help you see it. And then perhaps it comes back down on itself, or even, I don't know, does something like this. So from either side, it may be trying to approach that vertical line, but it's never going to quite cross it or touch it. That's what a vertical asymptote is going to be. Now, how do we find a vertical asymptote? Well, remember, vertical lines have vertical line shave. No, vertical lines have equations of the form x equals some number. So it turns out when we know we have a vertical asymptote, we can write out the equation of that vertical asymptote itself. It could be x equals 3. It crosses the x-axis at 3, and it's a vertical line. So remembering that that's the form of vertical linear equations, x equals some constant, an asymptote, a vertical asymptote specifically, let me specify, will occur at any x values that make the bottom go to 0, but make but do not make the top go to 0. It sounds a little bit funky. It sounds a little strange. The reason it has to make only the bottom go to 0, but not also the top, that one actually has something to do with calculus and limits, and we can't really fully kind of demonstrate it without the use of a limit. A hole occurs at any x value that makes both the top and bottom go to 0, if there are any. So that's going to be a hole. It's got to be an x value that makes both the top and bottom go to 0. And when you draw a hole on the graph, you literally draw the graph just like normal. You start drawing it just like it's an everyday graph. And then all of a sudden, when you get to the x value where the hole is, you just draw a hole, and then you keep drawing the graph as normal after the hole. That's literally a value that is just begging to be normal and be just like the rest of it. But it's not quite allowed because the bottom will go to 0 at that value, which is still an issue. But the fact that the top also goes to 0 means that something kind of special is going on. But we can't really fully talk about just how special that is without using any kind of more advanced math. That is just the way it is. So we have vertical asymptotes. Let me show you a couple examples. I'm using some specific numbers. Let's look at x minus 3 over x squared minus 7x plus 12. Let's find the domain and any vertical asymptotes or holes. So we're going to find the domain, any vertical asymptotes or holes, and then we're going to go about kind of graphing this thing. We're going to graph it. Of course, we're going to do more basic sketches than anything. Well, first of all, we need to find the domain, and the domain is actually going to be really helpful because when you're finding the domain, you're also going to be finding x values that make the bottom go to 0. That's just how it works for rationals. In any x values that make the bottom go to 0, those are your candidates for vertical asymptotes or holes. So finding the domain is really going to be doing a lot of the heavy lifting here. So to find the domain, we need to think about what x values make the denominator go to 0. So let's kind of just zoom in on that denominator here. I'll just steal it. I'll put it back in a moment. Now what we would want to do is we'd want to factor that denominator. We need two numbers that multiply to positive 12, and so they can both be positive or both be negative. When I add those numbers, I get negative 7. And it's clear pretty quickly that that means it's going to be negative 3 and negative 4. Those two will get the job done. So whenever we factor this thing, it's going to factor x minus 3 times x minus 4. x minus 3, x minus 4. And then we can look at a few other things. We can set those equal to 0. Remember, you would, but I think by now we can just say, well, that means x equals 3 is a root and x equals 4 is a root. X equals 3, x equals 4 are just clearly roots at this point. And so what we're going to have to do is we're going to have to say, oh, that is, or rather those are the elements, those are going to be the things that are not in the domain. Those are going to be the things that are not in the domain because they make the denominator go to 0. So let's restore this. The domain is going to be, it's going to look just like the last one did, kind of. It's going to be the whole real number line except for 3 and 4. So we need to go from negative infinity up to 3, union with, now it's got to also include everything between 3 and 4. And if you think there's nothing in between 3 and 4, you're wrong. Think of all the real numbers, not just whole numbers. And so everything in between 3 and 4, and then everything from 4 to the great beyond. And so there's your domain. Let's move this up to the top. Now the cool thing is, I'll also move this up here. The cool thing is by finding that domain, we've already started to kind of locate some vertical asymptotes. Let's zoom in on x equals 3. Zoom in. Let's plug x equals 3, not 4. Let's plug x equals 3 into the rational. So I'm going to put a 3 in for x. You'll notice you're going to get a 0 on top. 3 minus 3 is 0 on top. On bottom, we already knew that this should give us 0. You can do the quick mental math if you want, but we already identified 3 as a root or a 0 of this bottom. So it's already going to be 0. And so what this is going to be 0 over 0 here, that is going to make x equals 3 a whole. It's a whole now. It's not a vertical asymptote. But then we try x equals 4. We plug x equals 4 into this. On top, you're going to get 4 minus 3, which is not 0. On bottom, we already know that that's going to give you a 0. There's no escaping that. So that means you're going to end up with 1 over 0, which is not 0 over 0. Thus, x equals 4 is going to actually be a vertical asymptote. So this means x equals 4 is a vertical asymptote. Now that we understand the term vertical asymptote, we're just going to call it a VA. VA makes our life easier. It gets very tiring writing out vertical asymptote, horizontal asymptote every time. So let's sketch up a quick graph of what this is going to look like. Now, technically, when we graph, These rational ones are not so easy to graph all the time. Uh, there's a couple things we're going to want to do with the graphs, but mostly we need to, how should I word this? We need to maybe make a table and get some key values that are on the graph. Uh, we already know where vertical asymptotes might be. We're going to, after we do vertical here, we're going to study horizontal asymptotes and just exactly how they work. But for now, what we're going to do is we're going to look at just the vertical asymptotes. So for now, let me kind of take the reins on graphing here, and then I'll show you why some of it kind of made sense. So we know that x equals 3 as a whole. We know that x equals 4, though, is indeed a vertical asymptote. So right here, when x is 4, we're going to have a vertical asymptote. I'm going to go ahead and, I wish they had a dashed line tool. I'm going to attempt to just draw a quick vertical dashed line that roughly crosses here. And adjust what I do. Subtlety. And then here's what's going to happen. I can't fully explain why this happens until we study horizontal asymptotes, but it's still good for you to get kind of an understanding of what's going on here. It's going to approach this vertical line. It's going to keep getting closer and closer without ever actually touching it. Now, it turns out that the y-axis is also going to be a horizontal asymptote on it, or excuse me, the x-axis. So it's never going to cross the x-axis. And then it's going to do something like this on the other side. It's going to get ever closer to that vertical asymptote without ever actually touching it. So it's going to look a little something like this with one little extra piece on here. There's one little extra piece. When x is 3, there's a hole on the graph. So I need to go down there and basically make a hole. I'll do that with a little clever trickery. So it literally skips over that value. X equals 3 is not in the domain. So x equals 3 is not allowed to be on the graph. It didn't get the permission slip signed, so it doesn't get to go to the fireworks factory. It has to stay back. So x equals 3 would then just form a hole. And it's literally exactly what you think it is. It's just a value that's basically skipped over or ignored on the graph. So those are vertical asymptotes. I'm struggling hard to find like a joke I can make or something to kind of break up the, I don't want to use the word monotony, but just kind of the mechanical procedures we're going through here. Unfortunately, there's just not a lot of, can you guys think of a joke on vertical asymptotes? Can you think of a pun you can make out of that? Nothing interesting. I don't know. It just seems like a kind of a not so funny topic. But that's college algebra for you. The cool thing is if you took like a statistics course, there's all kinds of jokes we could make, lame puns. You guys, I could introduce you to my Scooby-Doo laugh, which is world renowned. It's a world renowned Scooby-Doo laugh. But there's just no way to bring my Scooby-Doo laugh here into the college algebra class. So you guys will forever go without hearing my Scooby-Doo laughs. I'm sorry. My dog kind of looks like Scooby-Doo though. And next weekend, not this weekend, but next is Halloween, and we're going to be dressing up my dog, who is a bloodhound, as Dumbo, and we're just going to use his own big ears as the elephant's big ears. And so maybe I will share a picture of my bloodhound with his Dumbo costume on. He's going to look really stupid, and I'm really excited to see it. So stay tuned, stay tuned. So horizontal asymptotes are exactly what they sound like. They're asymptotes that are flat lines. They are horizontal lines that the rational function gets close to, but never actually touches or crosses through, or anything like that. So now, as you can imagine, we actually just did one that had horizontal asymptote. The x-axis was a horizontal asymptote. But you can imagine now a horizontal line maybe something like this. I know it's not going to look brilliant, but, you know, as they say, that's life. So now a horizontal asymptote. Well, let's remember a few things. First of all, a horizontal line has an equation of y equals y equals b, where b is some number. A horizontal line is not going to be mx plus b because secretly it has a slope of 0, so the m goes to 0. So that means if you have a horizontal line, it's going to cross the y-axis at whatever value b is, whatever the y-intercept is, and then it's just flat after that. So, you know, a graph could look something like this. It could approach it from the bottom. And actually, there's all kinds of funky ones it could be. So it gets close, but it starts to kind of flatten out a little bit. Something like that. That's terrible. Hold on. Let me fix that. It's going to try to get closer and closer to that horizontal asymptote, but it's never going to be quite successful at it. And it's just going to keep going and going in that pattern. And then down here, it might do something funky. Who knows? But it's going to try to get closer and closer to that horizontal line without ever actually touching it. That's going to be the key takeaway of it. Now, again, the horizontal asymptotes are a little bit tough, mostly because whenever you have to figure out what the horizontal asymptote is, unfortunately, it is just a little memory game you have to play. It's a little memory game that you have to play, a little bit of set of rules you have to memorize. Now, later on, when you go to calculus, you'll learn that horizontal asymptotes are just found by taking the limit as x goes to positive and negative infinity. In other words, horizontal asymptotes are found by going along the x-axis and keep going and going and going and try to go off to infinity and see what the y values do. If the y values behave and they stay finite and they don't ever quite blow up, or there's some kind of way that they shrink to a certain value, that's going to be when we have horizontal asymptotes. However, if you make x extreme, if you make it more and more extreme, that's going to be the case where you're going to have no asymptote and the thing is just going to go off unbounded forever and just go down to this case, negative infinity. That's kind of what we were looking at with the end behavior test, actually. With the end behavior test, we were looking at what did the y values do as x went off to positive infinity? What did the y values do as x went off to negative infinity? Except for polynomials, a polynomial by itself is never going to have any kind of asymptotes, never. But a rational equation might have asymptotes. In fact, it's usually going to have at least one. And that's because a rational is not a polynomial, it's just constructed of polynomials. But by introducing that idea, you completely change the system. So vertical asymptotes are going to be tough. I'll just say that. Well, excuse me, horizontal asymptotes. To find a horizontal asymptote, an HA, you need to look at the degree on top, which I will just shorten and just call that the letter M. So remember, if you have some kind of rational, it can look like this. One polynomial divided by another. The degree on top is going to be the highest power you see on top, which in this case is 8. The degree on bottom is going to be the highest power you see on bottom, which in this case is 5. So continuing on, to find a horizontal asymptote, you need to look at the degree on top, M, and compare it to the degree on bottom, which I'm going to use an N to represent. So for this particular rational over here, M, the degree on top, is going to be 8. N is going to be the degree on bottom is going to be 5. And now you're going to have 3 possibilities. The first possibility is going to be that M is greater than N. The degree on top is strictly greater than the degree on bottom, which is exactly what's happening in this particular case here. In this case here, the degree on top, 8, is strictly greater than the degree on bottom, 5. When you have that, you're going to have no horizontal asymptote. The reason behind that, the degree of a polynomial is really one of the most fascinating things about it. The degree is one of the key factors or key things that tells you what the end behavior of the polynomial is going to be. The degree also determines not only the end behavior, it really determines how quickly the y values of a polynomial blow up to infinity or negative infinity. The higher the degree of the polynomial, you have a higher power, so suddenly numbers you're plugging in get blown up to larger and larger numbers. 2 to the 8th is a lot bigger than 2 to the 3rd. 10 to the 8th is way bigger than just 10 to the 3rd. So the higher degree, the highest power, really dictates the speed at which things grow. If the top degree is greater than the bottom degree, this top polynomial here is growing much faster than the bottom degree, that the bottom polynomial is growing. The bottom polynomial is trying to calm everything down, because if the bottom polynomial is growing, you're dividing by larger and larger numbers, and that's trying to kind of cool the jets a little bit. When you divide by larger numbers, it starts to shrink the entire thing. But the degree on top being larger means the top is eventually just going to outpace the bottom, and the whole thing is just going to blow up and go up to infinity. And that's exactly what we're going to see. That means there's no horizontal asymptote. There's no value that the function, that the rational function is trying to get close to, but can't quite dance near. No. It's just going to go off to infinity or negative infinity, and it's not going to care. So that's your first case. Your next case, is that the degree on top is smaller than the degree on bottom. So imagine I switched these, Let's see. Let's do some clever trickery here. Imagine I switched these for a moment. The first shall be last, the last shall be first. Let me give myself a little more room. And suddenly now the degree on bottom is going to be higher than the degree on top, like this. Shmeh, shmeh, shmeh. No, it'll make it larger. So we've done a complete 180. So now the degree on bottom is larger than the degree on top. So the bottom is actually blowing up and getting larger and larger and larger faster than the top can keep up. Since that's happening, think about it. Think if you do like 5 over 10, but then you do 5 over 100, 5 over 1,000, 5 over 10,000, 5 over a million, 5 over a billion. If you keep the top relatively small, but the bottom gets larger and larger and larger, the whole thing is shrinking. But it's not going to go negative or anything. It's going to shrink to zero. It's going to become zero. So that's what's happening with the horizontal asymptote as well. Now you're going to have a horizontal asymptote, or I'll just call it HA, of y equals 0. The horizontal asymptote is going to be the flat horizontal line, y equals 0, which remember, y equals 0 is the x-axis. Little side note. So that means that the horizontal asymptote then is the x-axis. The equation, the rational equation function, is going to approach the x-axis without ever actually crossing through it. It's going to get close, but no cigar. Finally, your third case, m is equal to n. Now, this one's actually going to be kind of funky. This one's going to be kind of funky. The horizontal asymptote will be y equals, or maybe I'll just say it will be the ratio of the lead coefficients it'll be y equals the ratio of the lead coefficients. So let's look at it, and I'll show you what I mean here with an example. Let's say you had the rational function (14x to the 7th plus 3x squared minus 2 over so you have 14x to the 7th plus 3x squared minus 2 divided by 5x to the 4th minus 9x to the 7th plus x cubed plus 4. Well, you'll notice the degree on top is 7. I'll circle it. The degree on top is 7. The degree on bottom is also 7. The lead coefficient on top, I'll put a little rectangle around it, is 14. The lead coefficient on bottom is -9. Remember, the lead coefficient is attached to the highest powered term. It is not just the first one you see. So For this problem, the degree on top is equal to the degree on bottom. The horizontal asymptote will be y equals, it's going to be a linear equation, a line, a horizontal line. It's going to be 14 divided by -9, or just y equals -14/9. So you have to draw a vertical line there. That's going to be what, -1.55555. I'll show you. Your vertical or your horizontal asymptote here is going to be this line, y equals -14/9. Oh. So it crosses here at -14/9, which is again -1.555555. The fives keep going. Whew. That's a lot to take in. Now, I attempted to explain a little bit why it makes sense. This first one, the degree on top is larger than the degree on bottom. The entire rational is just blowing up too quickly. Here, the bottom is blowing up faster than the top, so that's going to control it and give it this. But this last one, why is it the ratio of the lead coefficients when the degrees are equal on top and bottom? That is something that we would simply have to prove using a little bit of calculus. We'd have to use a little bit of calculus. We'd have to use limit theory if you really want to see why. And again, that is something that is a little bit annoying if we're being totally honest. It's annoying because it means that I can't demonstrate everything I want to you guys. I can't, show you everything and say, this is why this makes sense. We're just going to have to kind of live with it for now. So the unfortunate news that I have is that to understand these different asymptotes, the horizontal specifically, you're just going to have to commit it to memory. You're going to have to commit it to memory, which is kind of annoying. It's a little frustrating. I'll give you that one. But that is how it's going to be. The last type of asymptote, we've looked at vertical, horizontal. Now we're going to look at something called oblique, or also known as slant asymptotes. Oblique or slant asymptotes. And frankly, this one is just a little bit strange. It's a little weird. An oblique asymptote occurs when the degree on top is exactly one more than the degree on bottom. Again, why does it do this? Well, once again, I really have to just say we need calculus to really prove it. So, and I hate doing this. I don't just like throwing rules at you and saying memorize this stuff. Math is not about memorizing crap. You don't memorize what 147 plus 3,221 is. You learn the process behind addition, and then you know that you could figure out what the 147 plus 3,000 whatever I said is. You know how to do that. So memory is you need it when you're just beginning to learn a concept, but to really truly understand the concept, you have to go beyond pure memory of it. You have to justify why it makes sense. We can't do that here with oblique asymptotes or symptotes, which is, a pain in the butt. So for now, we're going to have to remember an oblique asymptote occurs when the degree on top is exactly one more than the degree on bottom. The oblique asymptote will be a line that has some slope to it. In other words, when we were doing horizontal asymptotes, we were writing y equals just some number. Y equals -14/9. Y equals 0. Here, you're going to have an asymptote that is in the form y equals mx plus b. Good old-fashioned American y equals mx plus b. And it's going to be exactly what it sounds like. Since it's an asymptote, it's going to be a line that the graph of your function is approaching but never quite gets to. But it's going to have actual kind of slope to it. So what that means is that you could have an oblique asymptote that looks something like this. It'll look like an actual line. Imagine it's dashed forever and ever, all the way till the end of time. And now this creates some exciting prospects, mostly in the form of, imagine you have a rational function that could look like this. It could come up. It has some curvature to it. And then it's going to try to snuggle up with the oblique asymptote up here. And it's going to get closer and closer. You know what? Let's do a better one. Let's do one that has a little more curvature. How about bang? It's kind of hard to draw, actually. It could even do something weird like this. It can cross it at some point, and then, so it can cross the asymptote, which is a little confusing. It can cross it at a few finite stages along the way. What matters is, as the graph goes on to infinity, as you go along the x-axis to positive infinity, it's now attempting to touch this asymptote, but never actually does touch it. We're going to see a few cases where that is going to happen, where it's going to cross through it, but that's because the asymptote is not really in play yet. It's not in play till we go to the extreme ends of the graph. So, how do we find oblique asymptotes? Why, polynomial division. That's correct. The way we're going to find oblique asymptotes and really I shouldn't pluralize it. There's only going to be one oblique asymptote. Let's find the oblique asymptote of this right schmear. -3x² plus 2 will be our top polynomial. And on bottom, we're going to have x minus 1. What we're going to do is we're going to do the polynomial division here. And then I'm going to show you a shortcut to it using synthetic division. Because think about it. You have this rational equation. You have a second degree polynomial on top. You have a first degree polynomial on bottom because there's an implied 1 here. So the degree on top is exactly 1 more than the degree on bottom. So this thing is going to have an oblique asymptote. So now technically you're literally dividing the top polynomial by the bottom polynomial. That's what you're doing when you form a fraction. So technically speaking, you could say it kind of looks like this, and you would not be wrong, where you're taking negative 3x squared plus 2 and you're dividing it by x minus 1. And you could do polynomial long division that way, but wait a minute. Looking at how it's written, this looks an awful lot like you could just use synthetic division. And that's true. In this particular case, you can use synthetic division. So we're not going to do it this way because we don't have to. We say no. Nope. We're going to use synthetic division. We're going to tell ourselves we're going to have a number in the upper corner, and that's the number based on bottom. Remember, if it's x minus 1, we put the number positive 1 in here for the synthetic division. Then we need to put the coefficients of this here, but we have to be careful. If we skip over any, see here we have an x squared term, and then we just skip straight to the constant. We skipped the x term. So what we can do, what we can secretly tell ourselves, kind of in the back end, is that there was a plus 0x here in the middle. It doesn't need to always be written, but by writing it here, the 0x, now that's going to guide my hand when I write out the coefficients for the synthetic division. You absolutely need the 0 here to represent it. Okay, so what we're going to do, we're going to do the synthetic division. We're going to bring down the negative 3. We're going to do 1 times negative 3, which is negative 3. We're going to do 0 plus negative 3, which is still negative 3. Then we need to do 1 times negative 3 again. You're going to get negative 3. 2 plus negative 3 is negative 1. So we're not going to have a remainder. Excuse me, we are going to have a remainder. What am I saying? There is a remainder. Now, a remainder sucks because normally when there's a remainder and we're trying to factor a polynomial, the remainder is the fly in the ointment and tells us, no, that's not actually a factor. So x minus 1 down here is not a factor of negative 3x squared plus 2. Guess what? In this particular case, it doesn't matter. It doesn't matter at all. You're going to ignore the remainder and you're going to tell yourself, all right, well, if I had done the division, this would create a polynomial of 1 degree lower than what we started with. We started with a second degree polynomial, so this would be a first degree polynomial with these coefficients, negative 3x minus 3. If you just take these here and translate them into this. The remainder does not become one of the coefficients. We ignore it. Well, guess what? This is your oblique asymptote. Ta-da! Remember, the oblique asymptote is going to be an actual y equals mx plus b type of line. So here is your oblique, not oblique, oblique asymptote. It has slope of -3, y-intercept of 0, -3. Phew! So you're not fully ready to start graphing these. We're going to look at graphing some of these next time on Tuesday. So on Tuesday we'll be meeting. We'll finish up this chapter 3. There's only a little bit left, and then we will spend the rest of the class reviewing for the exam. Then the following Thursday, October 29th, you're going to have your exam in class. You're going to have your exam. And the exam only covers chapter 3, and there's not a whole lot else to say about that. There's going to be an exam 3 review opening up this weekend, and you can work it over the weekend on MyLabs Plus. And yeah.